In this video, we're going to talk about vertical mass springs. This is where you have a block hung by a spring, or maybe it's on the ground and it's oscillating up and down. We'll talk about the period equations along with the energy analysis we're going to do. This is the most complex of them just because we have spring potential, gravitational potential, and kinetic energy involved. So now let's talk a little bit about vertical masses on springs, okay? So the basic equations are still the same, but now we're talking about a mass that is standing vertically on a spring. It could be like this. It's like suspended on top of a spring, or it could be hung from a ceiling. All right? There's a couple of ways. But then what you're doing is you're saying, oh, I'm going to stretch it and then let it go, and it's going to bounce up and down, basically, still in harmonic motion. However, the equation's still the same in terms of period and amplitude. However, some of the subtleties about the energy are a little more complicated because in the horizontal direction, there's no change in gravitational potential energy. So we don't have to deal with gravity because there's no change in height. However, in the vertical direction, the tricky part is there's three energies. There's the kinetic energy of the block, there's the spring potential energy, and there's also the gravitational potential energy. So the three forms of energy are very complicated, or more complicated, and the equations are more complicated to solve. But the setup is still the same process. It's still a conversion of energy. The total energy is constant, but it's being exchanged between the spring, kinetic, and gravitational potential energy. Okay? So you have to be a little bit careful on that scenario. So again, what's going to happen, let's take a look at this vertical example here, is this is sort of the equilibrium position. Now, the equilibrium position is a little tricky. The equilibrium position is where the net force is zero. That's where when mg balances out the spring force. See, the equilibrium position in a horizontal mass spring was when the net force is zero, but that's when the spring was relaxed horizontally. In the vertical direction, the spring is not relaxed at the equilibrium position. It's just counterbalancing gravity at the equilibrium position here. And then what's going to happen is it's going to bounce up and down like this. And it's going to go up and down with an amplitude A, and that's the vertical distance to the maximum stretch to the max compression there. Okay? So at these points here, like, you just have to remember, they're not symmetric. At the maximum stretch, it has a low gravitational potential energy, max spring potential energy, and no kinetic energy down here. And up here, it has the max gravitational potential energy, max spring potential energy, and no kinetic energy up here. Okay, when I not max spring potential energy, but it has some spring potential energy here. Okay, and here it has the max spring potential energy. And if you set the, h equals 0 down here, you can actually say it's no potential energy. Okay, so there's something different about the max height versus the max stretch. Okay, so it's a little bit careful on that energy conversion. Whereas like kind of on the horizontal mass spring, kind of the endpoints kind of had the same energies, just all in the spring potential. Now the energy is split up in a more complicated scenario. At the equilibrium position, it has the maximum kinetic energy. Okay, but it has it has some gravitational potential and some spring potential, because you have to remember it's still stretched a bit at the equilibrium position. The spring is not at its relaxed length there. Okay, so this is a little bit tricky. This kind of scenario, you just need to be very careful on all of the energies that are present when you're dealing with this vertical mass spring system. Okay, so let's take a look at some examples here. Suppose a block of mass 2 kilogram is hung from the ceiling with the spring constant, spring constant, so I have hung here, the spring constant K equals 100 newtons per meter, and this guy is a 2 kilogram block. You pull the mass downward a distance of 0.05 meters and let it go, and oscillates up and down. What is the maximum velocity of the block? Now, we actually need to start by solving what is the initial stretched length of the spring at this point here. So this is before, like this is the equilibrium position, right? So this guy here is equilibrium. And we're going to pull it down a distance of 0.05 meters and then let it go and see. Now, in order to know that this is, you got to remember, this 0.05 is not how much the string is stretched. You stretched it an additional 0.05 meters. You actually need to know how much is the spring initially stretched. And the way you do that is at the equilibrium position, you know that the spring force has to equal the gravity. So at equilibrium, you know that the spring force has to equal mg. That means, because you want the net force to be 0. So kx equals mg. So x is mg over k, which is 2 times 10 divided by 100, which is 0.2. So that means it's initially stretched 0.02. So when you stretch it an additional 0.05, the stretch amount is 0.25 meters. Okay? Now, let's do a little bit of energy conversion here. So this is the lowest point here. So this one, if we set h equals 0 to here, if we look at the energy down here, let's call this the initial position, the energy here. The initial energy down there, what kind of energy does it have? Well, he has no kinetic energy. He has no gravitational potential energy. And he only has spring potential energy, which we can figure out. It's 1/2 100. And x is how much he's stretched from the relaxed position of 0.25 squared. And that is 3.125 joules. Now, at the equilibrium position, be careful, because now he has some gravitational potential energy, he's got kinetic energy, and he still has some spring potential energy, because he's still stretched. So he has kinetic energy, gravitational potential energy, and spring potential energy. Now, I know the mass is 2, the v squared, then 2 times g, which is 10, and the height is 0.05. That's the distance from here to here, because that's how much you stretched it. And then 1/2 k, k is 100. And then the x is how much the spring is stretched at the equilibrium position, which we said was 0.2 meters, like that. So these two cancel, and I get v squared plus, let's just multiply these out, 2 times 10 times 0.05 plus 100 times 0.5 times 0.2 squared. I get 3. And that equals 3.125 joules. So that means v squared is 0.125, subtracting 3 from both sides. So v is the square root of that. And I get 0.35 meters per second. Okay? A little bit tricky. There's a lot of forms of energy to keep in mind. That's why I say it's a little more complicated, vertical mass and spring. Same principles, you just kind of have to be careful on that. Now, what is the maximum height the block goes compared to the equilibrium position? Well, so now we know the total energy is 3.125 joules. And let's prove this to you. Let's figure out what this height is, right? I need to know what this height is, because we have, up here, we have spring potential energy, and we have spring potential energy, and we have gravitational potential energy, mgh, right? And that has to equal. So the spring potential energy is 1/2 kx squared plus mgh. Now, we need to be careful on here, okay? Down here, we know we've stretched 0.05. So what we know is that we've stretched at 0.05 here. So his displacement, so if he goes up a distance a here, it's a little tricky to figure out what his compression is. He's going to be 1/2 k, and then his displacement is 0.2 minus what I'm going to call, like, is this, we'll call this distance here from equilibrium a. Okay? and then plus mg, and what is the height we're talking about is a plus this distance here, 0.05. What I'm going to show you is that this a should be 0.05, that it is symmetric. It's going to go up 0.05 and fall 0.05, and that has to equal 3.125 joules. Okay, so sorry that this one doesn't have enough space. I should have added more space on this one, and I probably will in the version that you have. So this is 1/2. What was the k? K was 100 times 0.2 minus a, plus the block was 2 times 10, which is 20. A plus 0.05. Oh, this one's squared. Sorry, I got to square this thing. Squared this guy right here. And that equals 3.125. And I'm going to multiply 1/2 times 100. That's 50 times 0.2 minus a quantity squared. I'll distribute this 20 as 20a. And then 20 times that is 1. Okay, this I'm going to have to distribute. It's 50 times, I'm going to expand this guy, a squared minus 0.4a plus 0.04 plus 20a. That's a binomial expansion there. So if I distribute, it's 50a squared minus 50 times 0.4 is 20a plus 2 plus 20a plus 1 equals 3.125. You don't have to do all this math. This is probably just more for illustrate for me to you. So I get 50a squared plus 3 equals 3.125. So then 50a squared is equal to 0.125, subtracting 3. And so a is the 0.125 divided by 50. And then you take the square root of that, and I get 0.05. So what I've proven to you is that he's also going to go up 0.05 meters. Right? And that's something that is not super intuitive, that it's going to bounce around that same point, but that's true. So the maximum height he's going to get compared to the equilibrium position is 0.05 meters. Okay? So you can shortcut that process for you guys. Now you guys know that the equilibrium position is the center. It's going to stretch down 0.05. That means it's going to go up 0.05. Simultaneous, like when it oscillates. It's like even around there. Even though the energy matching is very complicated, it's a lot more involved than but you can just use that result. You don't need to derive this result. I just wanted to use that example to illustrate that. That's how you would do it if you wanted to involve yourself with the algebra a little bit and prove to yourself why it definitely is up and down like that. Okay, let's look at the second example. Two identical blocks with mass m are connected by a string, which are hanging from a spring with spring constant k. So it looks like this. I have a spring constant. Here's an m. And here's another block m here. Neither block is moving, and the spring is stretched to distance x0. So this guy he's stretched to distance x0. If the string is cut so that one of the blocks falls, so I'm going to cut this guy right here, the resulting block and spring moves with oscillatory motion. So the remaining guy is now going to bounce up and down between here and here. So we're going to figure out what the amplitude of the motion is. Okay. So now this is supposed to be the equilibrium position once you cut this string, because that's where the, oh, actually, sorry, this is not the equilibrium position. This is, he's the stretched position, right? That's the maximum amplitude. So let me kind of redraw that a little bit to make it a little taller. So I have a block here. I have a block here. They're both m. Okay. But what's going to happen is once I cut this string, this guy's going to bounce around between the equilibrium position and here, right? And they want to know what the amplitude is here. So one thing we would look at is the spring is currently stretched x0. We want to know how much it's stretched at the equilibrium position. So let's talk about this first x0 here. So when both of the blocks are connected, all right, you can figure out how much the spring is stretched. I know they tell you it's x0, but you know that, like, if you look at this guy as an object, the spring force down here, the gravitational force of these two matches the spring force, right? like that. So kx0 is equal to 2mg. Right? This is what I kind of want you to kind of see. That first part is because right now when the two blocks are hanging there, before I cut the string upward force balances the gravitational force downward if you draw that free body diagram, right? Okay, so we know that this quantity is like held true. Now what happens is the equilibrium position here, the spring force also balances the gravity, but there's only 1 mg when the block is at the equilibrium position. Because again, at the equilibrium position, the forces should be balanced. But again, I've removed this guy once it starts moving up and down. So the equilibrium position is the spring force is just equal to mg. So his displacement is mg over k. Okay. Now, how does that relate to x0? Well, if this stretched position is mg over k, and like basically there's a relaxed length, we've stretched this mg over k, and this is, x0, we ultimately want to find that the amplitude is like x0 minus mg over k, basically. Okay, and you could write it like that. You could say like, oh, this distance here, let's say the relaxed length, I don't know what the relaxed length of the spring is here. Let's say the relaxed length of the spring is right there. Okay, so this distance is x0, how much you've stretched the spring. And we just showed from this equation, this distance here is mg over k. So then you can just take the difference. x0 minus mg over k is the amplitude. Okay. Now, you could have found that what I was going to show you here was that you could find that mg over k from this equation is actually equal to x0 over 2. So this is a perfectly acceptable answer, but you could also make this x0 minus x0 over 2. So it's equal to 1/2 x0. Okay, so this is another equation. Either equation would have been acceptable, but I probably would have used this one just because I think it would have been a little cleaner. Okay, now what is the maximum speed the block attains when it's attached to the spring? Well, now I want to look at the energy here. If I say h equals 0 here, then he has all spring potential energy. So I have 1/2 ka squared is the energy down at the bottom. So that's 1/2 k times 1/2 x0 squared. Oh, I'm sorry. How much he stretches, not sorry, I'm thinking horizontal springs. His stretch string length is just x0, right? That's what he said, x0 squared. Okay, so that's the energy at the bottom. And then at the equilibrium position, energy at the equilibrium, remember, he's got 3 forms of energy. He's got gravitational potential energy, he's got kinetic energy, and he has some spring potential energy because the spring is still stretched at the equilibrium position here. Right here, right? This is the equilibrium position. So what is the height? Well, it's a. So it's mg times a. But a we said was plus 1/2 mv squared plus 1/2 k. The spring stretched length we said at this point was mg over k, or 1/2 mg over k is 1/2 x0. So we could say 1/2 x0 squared. And this a is also 1/2 x0 because that's what we found here, right? And the height, see, the height from here to here is a, and that's also the amplitude of how much you've stretched it. So it just happens to be coincidence, 1/2 x0, right? So that's that, plus 1/2 mv squared, plus 1/2 k 1/4 x0 squared. That equals 1/2 k x0 squared. This ends up being probably a little bit of a hard problem to do as a demo. But we want to solve for v here. So this guy is 1/8 k x0 squared. This guy is 1/2 mg x0. Okay, plus 1/2 mv squared equals 1/2 k x0 squared. We're going to subtract the 1/8 k0 squared and subtract that to the other side. So we get 1/2 mv squared. 1/2 minus 1/8 is 3/8. And then minus 1/2 mg x0. Okay, I'm going to multiply by 2 and divide by m. So, well, just multiply by 2. That makes it 3/4 k x0 squared minus mg x0. and then divide by m and take the square root. So v is going to be all of this. This is kind of a little bit of a messy problem. I wasn't expecting it to be that much, but you can see why vertical mass springs are more complicated analytically. They just require you to involve more variables and more scenarios and be very clear on how you calculate the energy at each point. You need to keep track. There's a lot to keep track of what is the spring stretch at equilibrium? What is the spring stretch at the maximum stretch? What is the spring stretch in different scenarios, as well as keep track of the height of it? So vertical mass springs, while in principle similar to the horizontal mass springs, are just more involved analytically than the horizontal ones. Okay, what is the maximum height of the block above the equilibrium position? Well, that's just A. That's what we proved in the previous example. The maximum height above the equilibrium position is just simply A, which is 1/2 x0. We don't need to prove that anymore, because I'm just telling you that's something you can just know. And how long does it take for the block on the spring to go from the lowest position to the highest position? Okay, this one sounds hard. You want to know how far does it go from here all the way to here? But remember, like the pendulum one, that's half the period, because a period is to go up and then all the way down. But you remember your sine curves, half the period just to go to the up is going to be it's just going to be half the period to go from one end to the other. So this is just 1/2 of the period, and the period is a pretty easy equation. It's 2 pi root m over k, right? And m is the mass of the spring, and then the spring constant k, so that's just it. So this would be pi root m over k. So some of these equations are very simple. That's why the power of that period equation tells you a lot about the time of the motion. Okay. Thanks for watching. Please subscribe if you haven't already, just to like improve the quality of the channel so that it shows up more, so we can share this out with more and more students out there. The other thing is if you do need extra help, if you're needing maybe some more practice questions, more guidance on multiple choice questions, we do have program options to help you practice. Also run office hours. I answer questions for students, things like that. A little bit more just structured guidance. If you feel like you're needing some of that, go ahead and click the description below. There will be a link that takes you to a website where you can see about how the different programs operate for all the AP Physics and AP Calculus programs we run.